Hello, welcome. Today we're going to be talking about our next conversion factor, and it deals with how subscripts within a molecule can serve as molar ratios. All right, let's go ahead and get into it. So, we're going to start off here. How many atoms are in one water molecule? And we're going to split this up between hydrogen and oxygen atoms. In the first part of this video, I'm going to be working with water as an example because it's an example we're all really familiar with, and then we'll generalize this as a rule. All right, so how many hydrogen atoms do I have in this molecule? I have two. One hydrogen atom, a second hydrogen atom. How many oxygen atoms? I have one. All right, what if I have two water molecules? So here's my molecules. I have two individual molecules floating around. Maybe they're in a solution, maybe they're in deionized water. How many hydrogen atoms? I have 1, 2, 3, 4. How many oxygen atoms? I have 1, 2 of oxygen. Okay. What if I were to scale up? What if I had 35 individual water molecules? I'm not going to draw all 35, but if I had 35 individual water molecules, up here, when I had two water molecules, I saw I had 4 hydrogen atoms. There's 2 hydrogen atoms in each molecule. So if I had 35 water molecules, well, I would have 70 hydrogen atoms and 35 oxygen atoms. So the same pattern here. If I had 2 water molecules, I'd have 4 hydrogen atoms, 2 oxygen atoms. I can scale that up. If I have 35 water molecules, I'd end up with 70 hydrogen atoms, 35 oxygen atoms. I could keep scaling up if I want to an even bigger number. How would I figure out how many hydrogen atoms are in 1.5 times 10 to the 15th water molecules? Well, I know in every water molecule, I have 2 hydrogen atoms, so there's 2 hydrogen atoms times the number of molecules that I have. 2 times 1.0 times 10 to the power of 15 gives me 2.0 times 10 to the power of 15. Oxygen atoms, there's only one oxygen atom in every water molecule, so I'd have 1.0 times 10 to the 15th individual oxygen atoms in this many water molecules. So we can agree that there are always in a water molecule, or for water, there's always 2 times the number of molecules for hydrogen atoms and 1 times the number of molecules for oxygen atoms. If you do not agree with this statement yet, if you're not sure where this is coming from, you should stop the video and re-watch until you feel completely sure on this page. That's okay if you're not quite there yet. It's okay if you need to repeat. That means you're learning, you're engaged. But if you're not sure what I mean here, you don't want to move on yet. You want to pause and rework until you're in a good place with this statement. All right, so let's scale up again. One thing to notice before we do that, this statement we just agreed to, notice these numbers, this 2 times the number of molecules and 1 times the number of molecules, those are actually our subscripts. Generally for H2O, we don't write this 1 because it's implied, but these numbers, the amount of atoms, actually come from the subscripts. So an important thing to notice as we move forward. So let's scale up. So this time we're counting atoms in 6.0 times 10 to the 23rd water molecules. So for hydrogen, that's going to be 2 times however many molecules I have. In this case, I just happen to have 6.02 times 10 to the 23rd. For oxygen, it'll be exactly the same as the number of molecules. Excuse me. We can do the math here. This is equal to 1.204 times 10 to the 24th. All right. Is this a convenient number to work with? Hopefully we recognize that this is our man Avogadro's number. So instead of using this giant 6.02 times 10 to the 23rd, we can use more convenient language. So another way to ask that same question, instead of counting individual water molecules, I can just say 1 mole. Wherever I see Avogadro's number, I can just replace it with mole. So how many atoms are in 1 mole of water molecules? Well, 2 moles. Instead of saying 2 times 6.02 times 10 to the 23rd, I can just say 2 moles of hydrogen atoms and 1 mole of oxygen atoms. Remember, moles can count anything. So in my question, we have a mole of water molecules. Moles are a general unit. They're counting water molecules. And then when we count the individual atoms, we're counting 2 moles or 1 mole of atoms, not the whole molecule. So we're focusing in on the individual atoms. And then in the problem, we were counting entire molecules. All right, so that gives us these conversion factors that for 1 mole of water molecules, I have 2 moles of hydrogen atoms, which I notice is a subscript for hydrogen, or for 1 mole of hydrogen molecules, I have 1 mole of oxygen atoms, which I notice is that invisible subscript for oxygen. We generally don't write it. It's generally implied if the subscript is a 1. So in general, my conversion factor would be for every 1 mole of any molecule, the moles of the individual atom are going to be the subscript for that atom in the molecule. So if I had ammonia, my conversion factor would be for every 1 mole of ammonia, I have 1 mole of nitrogen atoms, again, an implied 1 here. And for every 1 mole of ammonia, I have how many moles of hydrogen atoms? You guessed it, it's a subscript. Of course, conversion factors, I know that I can write in either direction. I can flip the top and bottom depending on what value came before and what units I need to cancel. One thing to note here, in this case, I don't need to worry about diatomic. That's one common mistake I see. I'm not worrying that hydrogen is diatomic because I'm considering the hydrogen within a particular molecule. So you could consider the hydrogen within a hydrogen diatomic molecule, but I don't need to take into consideration that hydrogen doesn't exist alone. This is another point to pause. Make sure you're understanding. If you're not, that is okay. Rewind, go back, take notes, ask questions. Make sure you're understanding at this point. All right, we're going to move on to an example. So, my example here, How many moles of chlorine ions are present in 2 moles of calcium chloride? So calcium chloride, the molecular formula there, I see calcium is in group 2, meaning it would carry a charge of positive 2. Chlorine is over here in group 17, meaning it would carry a charge of -1. So the ionic formula would be 1 calcium for 2 chlorines to get a neutral molecule. I know this is ionic. I have a metal and a nonmetal. The electronegativity difference would be really big. And so if I put calcium chloride into solution, it would indeed dissociate into ions. So this works for individual atoms. It also works for ions. All right, so let's go through our normal process. The unit that I'm starting with is moles of calcium, moles of calcium chloride. The unit that I need to end in is moles of just chlorine ion, and my conversion factor. Do I have one conversion factor to go from the moles of a certain molecule to the moles of part of that molecule? I do. It's a subscript. Subscript. 1 mole of CaCl2 is going to be equal to 1, not 1, my subscript is 2 moles of chlorine. All right, so what would this look like? I start with the amount given, 2.5 moles of calcium chloride times, if I have moles of calcium chloride, what needs to go on the bottom in my next step? The same exact thing, moles of calcium chloride. In my conversion factor, I see that moles of calcium chloride relate to moles of chlorine ions. Now I can fill my numbers, and it's the same numbers I just came up with in my conversion factor. So 1 mole of calcium chloride, 2 moles of chlorine ions. So this is equal to 2.5 times 2, which is 5 moles of chlorine ions. All right. This gives us a couple more conversion factors to add to our overall document. We've done Avogadro's number, we've done molar mass, we've done molar concentration. We now see that subscripts can relate the moles of a single element in a molecule to the moles of the molecule, their moles of an ion, to the moles of an ionic substance. So this could be a single ion like chlorine, or it could be a polyatomic ion like nitrate. Okay, at this point, you can stop the video and start doing your homework. I'm going to, at the end of this video here, I'm going to go through IB problem 1 on the homework. My suggestion is that you come back to this only if you need it. My suggestion is that you try this homework problem first. Try on your own first. But I'm going to end this video walking you through this problem so that you feel confident moving forward. All right, so what is the number of carbon atoms in 12 grams of ethanoic acid? And they give us the molar mass. So let's go through a process. The units I start in, the units I end in, the conversion factors. So I'm starting in grams of ethanoic acid. I need to end in number of carbon atoms. Okay, interesting. Do I have a conversion factor to go directly from grams to number of atoms? I don't. So I'm recognizing that I'm going to have to move between moles. Moles are always a go-between, so grams to moles using molar mass. I then recognize that I'm going to be in moles of ethanoic acid. So I'm going to have to go between moles of ethanoic acid to moles of just carbon, because I see that the problem is interested in just carbon on its own. And then I'm also going to need to find the number of individual atoms. So I'm also going to need Avogadro's number. Okay, so I have a plan. Let's see if I can execute it. I'm going to set up my conversion factors. I start with the amount given. The amount given is 12 grams of CH3COOH. Even more so than before, it's really, really important that you specify not only your unit, but your unit of what for these types of problems. In this case, my unit is grams of the whole ethanoic acid. All right, if I have grams of ethanoic acid here, what needs to go in the bottom in my next step? You guessed it, grams of ethanoic acid. Well, grams of ethanoic acid, I see my first conversion factor. I need to relate that to moles of ethanoic acid. So let's fill in these numbers. They give me the molar mass, 60 grams of ethanoic acid. They actually give me the relative molecular weight, which I know is also the molar mass with units, to 1 mole. All right. If moles of ethanoic acid are on top, what needs to go on the bottom in my next step? Moles of ethanoic acid, you guessed it, so that we can cancel. All right. So I see in my conversion factors, when I have moles of ethanoic acid, I'm going to need to get into moles of carbon. Okay. For every 1 mole of ethanoic acid, how many carbon atoms do I have? Well, we actually wrote this out more as a condensed structural formula and not a molecular formula. So you don't have a subscript, but you have 2 individual carbon atoms. Okay, almost there. I see right now I'm in moles of carbon. I need to get into number of atoms. I have 1 more conversion factor. If I have moles on top, what needs to go on the bottom? Moles of carbon atoms. And then number of carbon atoms would go on top. For every 1 mole, I have 6.02 times 10 to the 23rd atoms. Let's check my canceling. Grams of ethanoic acid cancels with grams of ethanoic acid. Great. Moles of ethanoic acid cancels with moles of ethanoic acid. Awesome. Let's see. Moles of carbon cancels with moles of carbon. And I am magically left with number of carbon atoms as my unit. All right, the only other trick to this problem is this is a paper 1 problem, meaning there is no calculator allowed. No calculator, you say, but look at these giant numbers. All right, this is where we need to do a little bit of mental math. So let's take a look at what that would look like. I'm going to make this just a little bit smaller if it lets me. Okay, let's make this just a little bit smaller so we have some space to work. All right, so if I take a look at my multiple choice answers, I can obviously, if I'm dealing with number of atoms, even if I didn't have time to do all this math, well, A and B just don't make any sense. If I'm dealing with individual atoms, 0.2 of an atom, atoms are so teeny, teeny, tiny. How would you have 0.2 of an atom or 2 carbon atoms in 12 grams? That doesn't make any sense. So we're left with C and D. All right, so let me figure out what this math is going to look like. I'm going to have 12 times 1 times 2 times 6.02 times 10 to the 23rd all over 60. Let's see if I can do some canceling here of numbers. Well, I see 12 and 60 cancel into 1 and 5. Okay, that's good. That's good. I see 2 times 6.02. That's about 12 something. So that's going to be about 12 divided by 5 times 10 to the power of 23. Well, 12 divided by 5, 5 times 2 is 10. So 5 times a little bit more than 2 would be 12. So 2.3 is the answer that makes more sense to me. 5 times 1.2 wouldn't quite get me there. So the answer that makes sense if I divide 5 by 12 in my head, the answer that's closest is 2.3. So I think this last step, it's a little bit of a leap, a little bit of mental math that you have to do here to get to D. Let me know what questions you have. Hopefully that makes sense. All right, have a great day.